Hi, thanks for watching. This is my oops. Oh, I guess I don't need that on. This is this is my third live stream for making this generative art project that I'm trying to do. So, I'll just show where I'm at right now. So, currently I built this on the first live stream. It makes a simple shape um to review real quick. Um I'm just going to show what I'm trying to create. So I want to make something like this. This is just a style I do. It's all these shapes that kind of fit together geometrically. And it has really simple rules. The first rule is just that none of these shapes touch. They kind of follow each other, so the curves are parallel to each other. It's not perfect because I did it with marker here, but that's what I'm going for. They fit in with each other. And finally, each curve either has two sides, or each shape has curved sides, and it either has two sides like this one, two. This one also has two, one, two, or it could have three sides like this one, two, three. And that's basically the only rules. So I'm trying to come up with an equation for drawing these shapes. The first thing that I found that applies is Bezier curves, which I like because you can see here it gives you a random curve. I don't want to just use parabolas or circles because I think that will restrict the curves, so that there's all sorts of interesting shapes these make. Like, let's see. I'm trying to find an interesting curve, one that looks really interesting. Maybe I'll click over. There's a bunch of them here. So, this is a good example right here. This one kind of looks like a wave, and so that curve maybe could be like a really large circle or something. This one maybe could be a circle. You could definitely do it with a parabola. But this curve where it starts out kind of flat and then goes up and then flattens out again, an S-type curve, you can't really do that with a parabola. But I think you should be able to do that with these Bezier curves. I'm not sure if you can use a quadratic Bezier curve, which is what I've been doing, these ones right here, or cubic. Yeah, some higher order Bezier curve might be needed for those cool shapes. I haven't really thought that out too much, but I started with quadratic. So using the quadratic Bezier curve to do this, I got my initial code. Here's an example of one. I'll run it again. And this code it attempts to draw one of these shapes by first, it picks two random points and draws a Bezier curve between them, and then it draws another Bezier curve, and they're supposed to have the same endpoints, so they should connect. But when I run it, there's a few problems with it. So here's the first curve and the second curve. So it always connects at one of the endpoints, but there's another endpoint where it doesn't connect. So that's one of the problems. Another problem that it has is that these curves often overlap each other. I'll try to see if I could generate a shape that does that. So it always connects at one point. At another point, it doesn't quite connect. And that looks pretty good. That's a really good looking shape. Let's try to do one more. Another problem is that sometimes the lines are almost straight. There we go, that one overlaps. So then there's this overlapping problem. So I realized that I need more constraints on how I make these curves. The way you make the curve is you dictate two control points. So like for this first curve right here, or not control points, endpoints. You have first endpoint here, second endpoint here, and then there's a control point out here. And then you kind of just draw a line between each endpoint and the control point. And then you move incrementally along the line, and then you draw a point at the halfway point of the line, and then you keep doing that around the whole curve, and then you can trace. This is the line that the midpoint makes. So that sounds kind of confusing, but you can see it here. They have I think they have an animation on Wikipedia. Here we go. So this is what the quadratic one looks like. So here's the first endpoint, here's the second endpoint, here's the control point. There are these gray lines between the control point and each of the endpoints, and it moves incrementally up each of the gray lines, starting at one endpoint and also the control point, and then it draws that green line between those two lines, and then whatever the midpoint is, not the midpoint. So I guess you move the distance along the line. So they have this t value. When t equals 0, the point that it's drawing on that green line is all the way down at the p naught end of the point, and when t equals 1, it's all the way down at the other end of the green line. So that's how it's drawn. So, but you can see from that curve that I need more constraints on how I draw that. So that's from the first live stream. And also that doesn't look good how wide that is right there. So I had that from the first live stream. In the second live stream, I came up with this diagram, which shows the process of how I want to create it. So the first step is I generate these orange points here. Those are the endpoints for the Bezier curve. And I draw a green line that goes between those endpoints. So I think I've actually written this down in a notes file. If I go back into the generative art project, maybe here, I should just have one notes file. Okay, yeah, here are the steps. Generate 2 random endpoints, so that's what the orange points are. Those are the random endpoints. They could be anywhere in space. Then calculate the equation of a line between the endpoints, so that's this green line right here. Then calculate curve 1 control point bounding box, so that's a box. 2 of the sides are perpendicular to this green line that goes between the points, and the other side should be parallel to the green line. This distance right here, calculate curve 1 control, use line with control points with 30% of the ends chopped off. Oh, I see, yeah. So if the control point was actually outside of this yellow box, then you could end up with an ugly curve. So, oh man, I forget though. I guess that 30%, yeah, is just some amount inside. So this 30%, this means that this, if, I guess I'm going to edit this here. So if we, you make the distance of the first line d, make that smaller. Okay, so the distance of the first line is d. Then the distance of this yellow line, so put another line in there. Couple endpoints. Okay. And then let's put in that text. So what this should be is 0.7d. Okay. Zero point 0.7D. Okay. Okay. So, I guess this could kind of be two steps. Is it first generates that red bounding box, and then it generates the yellow bounding box. Yeah, I think that should be fine. Now we need another, so we get this control point. Generate bounding box for curve 2 using point from curve 1 as corner. So I guess the point should be something like this. Huh. I wonder if I could do... So I guess it should be in the yellow box, but I think we want to then move this second bounding box. Just trying to think, where would I want the second bounding box? Maybe we could put in a rectangle. Oops. Okay, just trying to line up this box. Okay, so I think that the new point should be somewhere in that box, but we also want an area where the point can't be. Because if the point ends up somewhere here, no, I think that would be fine. It would be a straight line. Well, I guess that will be fine. I can go with that as the second bounding box for now. And then if the shapes don't look good, then I can always change it. So, that file was the initial curve. The new file that I made on the last live stream was I guess single shape.py. Okay. Okay, so let's see what this runs. Py single shape.py. Oh, okay. Great. So it generates two random endpoints, draws the endpoints the same way that I did here in this picture. So we got the orange endpoints. Now, oops, run that again. And then it turns around and draws that blue line. I guess I'm trying to draw the bounding box. So I'm probably going to need to calculate some angles. I remember last time I was trying to turn, maybe so that it would be at 90 degrees with this. I guess I can just calculate the corners of the bounding box. So that'll be the next thing to do. Okay, so I'm going to take a quick break. Okay, so I have green line and these two orange points. So I guess the question is, how do I do that? So okay, generate random endpoints. Get distance between points. Shifted to, what's that mean? Okay, so the difference between x's and the difference between y's. So shifted to, okay, so the shifting just puts one point at the origin. So if shifted, okay, so if the shifted x value is greater than 0, if x is greater than 0 and y is greater than 0, so if we're in the first quadrant, cos theta is x over hypotenuse, sine theta is y over hypotenuse. Okay, so then you get theta. Otherwise means if y is negative. I did this before. So let's see. Well, it prints theta. Oh, so that's theta. So it turns 1.67. I don't know. Let me watch that again. See what it does. Okay, so dot, draw, dot. And then it turns just over 180 degrees. The turtle thing is always pointing directly to the right. Okay. Okay, so makes a dot, changes pen color to green. It says it turns theta degrees. Does it turn at all? No, the only time it turns is after it finishes the second shape. Goes to the second endpoint. Then it makes a dot. So I guess we could forget about that turn-in stuff. Leave all that theta stuff out. Forget about that. Then want to pick up the turtle. What pen color should this be? So the first bounding box is yellow. It's 70% what the full bounding box should be. So this will take some geometry. So let's see. We know this, right? And we want to find, there's this rectangle that goes around it. Okay, oops. Okay. Now, is there an easy way to draw a rectangle in Turtle? Okay. Yeah, so I guess I just have to pick up and go to the corner location of the rectangle. So, I'm going to try to do some math real quick. Go to Google Docs. Okay. Okay, and here's the math for calculating the rectangle corners. Okay. Okay. Endpoint 1, x1, y1. Endpoint 2, xy, x2, y2. Now, distance between points is just equal to, actually gonna insert an equation. How do you do an equation? Alt E. It used to be Alt-I-E. Oh, yeah, that still works. Okay, so dist between points is just equal to the square root of x1 minus x2 minus x1 quantity squared x2 minus x1 square that plus y2 minus y1, okay, square that. Okay, now we have our distance between the points, and the distance of midline of bounding box 1, which is the bounding box for the first control point. Okay, so how do we find the distance? It's 70% distance between endpoints. Okay, so the midpoint should be the same. How did I find the equation of the line to draw? I don't think I did. N.1. Yeah, it just gets the distance between the points. So, then you could do some trig. So there's endpoint. So this is okay. So endpoint 1. Copy. Put it over here for endpoint 2. Now you want to find the distance between those. I guess just the equation of the line. So how far should it be? It should be along the line, in the direction of the line. It should go towards that second point. Ugh. Should go towards that second point, but stop at 30%. So, point 1, draw point 1, draw point 2, draw this line between them. Now find that point. That's 30% inside. So, the first thing is the equation of the line between 2 points. So the first thing is, obviously you get the slope, m equals rise over run, so y2 minus y1 over x2 minus x1. So that's the slope. And then point slope form, you have y minus y2 is equal to m times x minus x2. I believe that's what it is, so if we plug it in, so now over here we get, y minus y2, well, yeah, y minus y2 is equal to y2 minus y1 over x2 minus x1. So making it a fraction, y2 minus y1 over x2 minus x1, and then that whole thing times x minus x2. Okay, so you simplify and you get y, yeah, this is right. So simplify it, now you get y equals to this whole thing. Okay, that m times x, and then plus, well, minus that whole thing times x2 and plus y1, so minus that whole thing times x2, and then plus y2. So that means that this insert the equation, that is equal to b, and m, we already have m. Cool. So now we have an equation. Now we have an equation. Okay, and now we want to find a new point. Now we want to find a new point, two new points, which is so the two new points we want to find are I'll just call it x3, y3, and x4, y4. So I'll find these two new points, x3, y3, and x4, y4. So which direction should it go in? So, We want the difference between the distance between the points. So, how to find the distance between the two? Oh, so this thing okay, so now I want to find our two new points. That's the distance between the two. So take that, multiply that by 0.7. How to find a point that lies on a line segment. How to find a point that lies on a line segment. Okay, so we want to find two new points. 0.15 times the initial distance is the distance between the endpoint of the initial line, the endpoint, and the edge of the bounding box. How to find the midpoint? Maybe that's what I want. The midpoint between the two endpoints of the curve. How to find midpoint of a line segment. If you know both ends, you can find the midpoint. Halfway between the two x values. Oh, is that it? Add the x coordinates divided by 2. Add the y coordinates divided by 2. Okay, well that's pretty easy. So, midpoint of line between 2 points. 2 endpoints of our Bezier could be defined as, put a new equation in, so we do x, do a fraction, x2 minus x1, put that whole thing over 2, same thing with the y's here. Okay, so now we got that control point. Okay. Well, that's not a control point actually, that's the midpoint. And now we want to do a square based off that midpoint that is aligned with the line between the two endpoints of the curve. So, got the midpoint of the line, so I'm just gonna, wonder if I could add to this. Yep. So let's just make that midpoint right here. There we go. So, we've got the endpoint. Now what do we want to do? I want to draw a line from the endpoint that is, it goes along here. I want to find that point. And I get that by doing 0.35 times the distance of this whole line. And that's how far I want to go up there. So if we have that, now this distance, 0.35 d1, times d1. Oops. Okay, that's that distance. Now, then there's the midpoint. Okay, there's that distance. We have our midpoint. That's the unknown point. We know the equation of this line. We know the equation of that line. I'm just trying to think, how do we find? Now we want to find this point. How do I find that point? Have that. I want that. I know this point. Oh, and I know the end point. So if I know this point and I know the end point, I think I should be able to figure out a proportion. So if we say that x3, x4. Okay, just a sec. I'll be right back. Okay, so I'm back. Now, so I found the midpoint of the line between the two endpoints. Now I want to find these new points, x3 and x4, y4. Which are that distance along the line. So I'm going to go back to this drawing and yeah, and now we have that distance. Okay, and then this distance is 0.35 times d1, 0.5 times d1. Okay, we also know these endpoints here are, say it's x1 and y1. We know the midpoint points are obviously x sub m, x sub m, y sub m, and that's known. Oops. I want to move that. Okay, and then this is going to be x3, y3, the green point. Okay, now how to find x3, y3? Well, to get the midpoint, you get the difference between the points. Divide by 2. So here you could get the difference between the points. Okay, so if you want the equal distance, you divide by 2 or multiply by 0.5. Here, you multiply by 0.35. Or 0.7 I would want to multiply by. So I believe, so that's the midpoint. And we could say that that is x sub m for the midpoint, y sub m for the midpoint. Now, green point on line between end. This point is the intersection of line between endpoints and first bounding box. So how to find the green point? You do x1 minus x sub m x1 minus x sub m. Oh, I guess I'll put this in an equation. Okay, x 1 minus x sub m. Guess I don't want a fraction. Okay, so I think there's gonna be some weird stuff with negatives or whatnot, but for now, I'll just try to implement this. So, put that on that side, this on that side. Okay, so we have the endpoints, we have the distance between points. Now let's get the midpoint is equal to 0.5 times, what was that noise? Guess it's still going, that should be good. So 0.5 times the difference, so and 0.1 of 0, 0.5 times and 0.1 of 0 minus and 0.2 of 0. Oh. Okay, so 0.5 times that, and then the other part of the tuple is just the same thing, but with the y elements. Okay. Now, I'm just going to call this green point. Is equal to, so x1 minus xm, so times 0.7, so x, so endpoint 1 of 0 minus midpoint of 0 times 0.7, and then comma, and then that same thing. Okay, and then total dot go to, so it goes to the second endpoint. Okay, makes the dot, then I make the green point blue, then, okay, so, oh, pick it up, then go to, green point, guess I'll call this the red point. Okay. And then turtle dot 20 red. Okay, Now let's see what this does. Where's the turtle window? Well, that's weird. Just open up a new PowerShell. Okay. So that's off. Let's see if it's on sometimes or if it's just off every time. That's off. Okay, so it's way off. So if go to the red point, let's go to the midpoint. Make that red. See what that looks like. Well, that's not the midpoint. So, oh. So these should be the Y values, not the X values. Same with those. Save. And what's that look like? Oh, exit out of there. Run it again. Still totally wrong. Midpoint. Oh, you add and divide by 2. Not subtract and divide by 2. Okay. Now let's see if that works. Cool. One more time to test. Okay, that's a nice end point. Now, let's see if the red point is at the proper location. Nope, that's off. Try it again to see what happens. Off. And one more time. Off. So, how do I get the red point? Endpoint. Oh. Didn't fix that, so that's still subtracting. Okay. Now if we add them instead, see what happens. Should increase the speed of this so we don't have to wait so long. Okay, that's off. Oops. And I spilled my coffee. Just a sec. Okay. So, faster speed. Let's try it. Wrong. 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 So, instead of that, I could find the angle. So, direction, so the distance between the endpoint and the midpoint. Distance between the endpoint and the midpoint. So, So first I guess I could do endpoint 1 of 0 minus the midpoint. So that time minus the midpoint times 0.7. What if I just try that? Doing the minus instead. It's a little off. That one's very off. So, get a point along a line that is a certain distance from another point. Let me explain the answer. Start point, end point. We need to find a point, a distance d from the start point towards the end point. Yes, that's what I want. The distance between the start and end point. So the ratio of the distances trying to think how this would apply to me. Oh man. So I already know how to get the distance. Then the point xt, yt is 1 minus t. When t is between 0 and 1, the point is on the line. Okay. So here the ratio is equal to 0.7 because that's how far I want to go along the line. 0.7, no, 0.15 is how far I want to go along the line. Then the end point. Now we could say this is the red point. So x is 1 minus ratio. Multiply that thing times x naught. So end point 1 of 0 plus times endpoint 1 of 0 plus ratio times endpoint 2 of 0, and then comma, and the other point is 1 minus ratio times endpoint 2 of 1 minus oh, yeah, minus ratio times endpoint. This would be endpoint 1 of 1. This would be endpoint 2 of 1. Okay, that looks good. Let's see where the red point is. So it closed immediately. Midpoint isn't a tuple, but endpoint is a tuple. Or red point is a tuple. So I guess we gotta take a pair of parentheses off of the edge. Point 1. What? Oh, red point is equal to that. Duh. So the red point is slightly off. There it was right on. Slightly off. 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 Make sure that that line is commented out. That looks pretty good. Off. 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 Okay, so this guy is another way. I normalize this to U is equal to V over the magnitude of V. If you want it in the direction of x1, y1 or x0, y0, plus d times u. Man, I don't know how to do vectors. Yeah, you want to find C. XC, YC. B equals D times B minus A. B is the end point. A is the starting point. B is the end point. Okay, so we'll try it a different way. So, starting point, end point. So, define get red point start end. So red x is equal to 0.15 times the distance between points. Okay, so red x is equal to 0.15 times the distance between points times b. Okay, so end point 1 of 0 minus, so we'll say this one starts at endpoint 1 and ends at endpoint 2. 0, so b minus a, and then to that whole thing you add a, endpoint 1, 0. Now, to get y, it should just be exactly the same thing. Okay, 1 of 1, and then red point is equal to red x, red y. Unsupported types for float and list. Oh. That was not supposed to be a bracket. Okay. Line 293. Turtle dot go to red point. Red point is equal to red x, red y. So why isn't that working? So put the debugger in there, see what's going on. Okay, run it again. Now, what's the red point look like? Okay, so the red point is just way off. 0.15 times distance between points. Okay. So it doesn't show any error. It's just that the red point isn't anywhere on there. Well, there it's on there. There it's not. There it's not. There it's not. Print endpoint 1 and point 2. Okay. Yeah, that's not right. So, how come the one time it did print on there? What do I have to do? Huh. So, distance, so endpoint 2. Start at endpoint 1, go to endpoint 2. Minus endpoint 1, then plus endpoint 1, d times the difference. Print distance between points. So 18 minus 28 minus 1, so 18. So do 18 squared 0.5. Then inside goes 18 squared plus 13.3. Oh, no. 31 minus 25 plus 6 squared, so 36. Should be a distance of 18. So the distance is correct. Okay. Run it again. Oops. So 2.57. Oh. Okay. Now run it one more time. Okay, so that's incorrect. I think you need to check x naught is greater than x1. D2. So how do you get C if you know A and B? You're looking for x sub C, which is D2. D2 over D. So yeah, the ratio of the points, which in my case is just 0.15, x sub A minus, so that's a little different, x sub A, so the x point of A minus the x point of b, multiply that by the distance, subtract it from endpoint 0. So then endpoint 1 of 1 minus, and then take off that term at the end, save it, open up a new PowerShell, oh that's wrong, did I save this? Yeah, it still goes way off. So new point 61, 177. What is going wrong here? XC, D, and D2R. It's a sine of AB. So if we move endpoint 1 to 0, then shifted to endpoint 2 minus endpoint 1. So that's the same as moving endpoint 1 to 0. Okay, now so shifted to new point is equal to, okay, and the first term is shifted to endpoint 2 shifted times zero 0.15. Should be scaled down. Actually should be 0.85. And the other one is shifted to of 0 times 0.85, shifted to of 1. Okay, and then shifted to, we want to add endpoint 1 to shifted 2. Okay. And that should be our new point. Okay, now I think that should work. That at least makes sense in my head. So, not new point, this will be the red point. Okay, now let's see what it does. Slightly off. Slightly off again. Oh. Shifted to 0 times 0.85. Shifted to of 1 times 0.85. That's not right. That's not right. I don't get it. It seems like then if you shift one of the endpoints to 0, 0, It's, you do the difference between the points, multiply by 0.5. So you add endpoint 1 of 0. I don't see why this doesn't work. So it seems like the x distance is off. Maybe you need to do one by 0.85 and the other by 0.15. Let's see if that will work. And I could tell that's what I want, and it's just off by that amount. Okay, what do I have to do? So I have to get these red points. I'm gonna take a minute and not say anything and just try to draw this out on paper so that it makes sense to me. Okay, now if we want to put point P1 at 0, 0, now P1 is at x1, y1, point 2 is at x2, y2. Now if we want to put point 1 at 0, 0, putting point 1 at 0, 0, then you multiply okay, so now if P1, which means now 0 minus x1 P is at 0 minus x1 plus x1 x1 minus x1 y1 minus y1. Okay, now that's P0. Now P2 0, it's P1 0. Now P2 0 is equal to x2 minus x1, comma, y2 minus y1. So that's P2 0. Now, yeah, why won't that work? So you can just do x2 minus x1. The difference between those. So x2 minus x1 is to 1 as the new x. that's x3 is 0.15 times the shifted p2 points. And then at the end, you have to add on. So this will be slightly negative. You already subtracted x1. So now you have to add x1. So red point is equal to red x, let's say endpoint 1 of 0 plus 0.15 get rid of that distance between points. Now save that. Okay, and what's this red point look like? Okay, still off. Oh, that should be a plus. Okay, and again. Oh, that's at the right place. Try it again. Oh, also the right place. Nice. Okay, that's what I want now. Now, so we have the first red point. Now let's get the second red point. Is equal to, it's that. So 0.15 should be 0.85. Get that. Put it inside of a tuple. And 0.85. Okay. Now, second red point. Okay, so then turtle. Now pick up the turtle. Now turtle dot go to second. Oops. Dot go to second red point, and then make another dot. The same features. Okay. Now run it again. Does it get both red points? Oh yeah. Okay, now let's make the red points smaller. Maybe 5. See what that looks like. Oh, only one of them was 5. Make it 8 instead. Okay. Nice. So now that we have the red points, what do we want to do? What do we want to do? So I have red point 1, red point 2. Now I want to make a bounding box with those points. So I guess I want to find a point that's parallel, so perpendicular to this line. How to find the equation of a line that's perpendicular to another line and intersects a point. Find the equation of a line perpendicular to another line that intersects a point. So I know the equation of my line. Convert the equation to slope-intercept form. Old slope, perpendicular slopes. Perpendicular slopes must be opposite reciprocals of each other. Oh, and then use the point that it knows it goes through. So slope has to be a reciprocal. So now get slope of line perpendicular to line between endpoints. So pretty sure I got that slope between up there somewhere. No. Okay. So slope endpoint line slope is equal to just the difference. Endpoint 2 of 1 minus end. So it's just the difference between the y's divided by the difference between the x's. Oh, endpoint 2, endpoint 1, endpoint 1. So that's the slope. No, perpendicular slope is just equal to that flipped. Okay. And endpoint line. I'll actually just put that right up above. Endpoint line intercept. So we know that it goes through. So when y is equal to endpoint, the y at endpoint 2, y equals mx plus b. So then you do minus endpoint line slope times end point 2 of 0, which is just the x value. And then oh yeah, that's it. So okay, endpoint line intercept, perpendicular slope. And then we know that the line we know that the rectangle that the first bounding box intersects the endpoint line at the red points. So we can use this to get the intercept of the line we're trying to draw. Okay, so now the perpendicular slope, so we can just say perpendicular line, intercept. Well, there's red point, so perpendicular line, intercept 1. And so that's for the first one is just equal to red point. So just going to change this to be red point 1. Going to change this one to be red point 2. Red point 2. Go down here. First is going to be red point 1, red point 1, red point 2. Perpendicular line, intercept 1 is red point 1 minus perpendicular line slope, and that should be the y value of red point 1. And then the perpendicular line slope, perpendicular slope times red point 1 of 0. So the x value of red point 1. Okay. And then should be the same thing for getting perpendicular line intercept 2. Okay, so the second intercept is just that. Okay, now we have the equations of two lines. Now, what direction do you go in now? So the equation of the perpendicular lines, pretty much the equation of the lines that define this outer rectangle. And I want to find the corner points of the rectangle. So I could do the same thing, start at that point, move along the line, some distance. How did I do that before? Red point. Oh, just got the difference in the points and moved some distance. So move a distance along a line. So back to this, we can say that if we move just gonna call this bounding box. So if we move a distance, gonna start at red point 1. So x, okay, equation, and red point 1 looks like this: x sub r1, comma x sub r2. So that's the first red point. Move along line. Distance. Now that should also be 0.7 the initial distance. So equation of line between two points, distance between points. I'm just going to call this value d1 so I can refer to it easier. Move along the distance. 0 should be 0.35 times d1, and that's because the bounding box should be square and have dimensions of 0.7 times d1, 70% of the distance between the endpoints. So if you do half of it, it should be 0.35. And it's just half because you move in one direction. So move along distance 0.35 times d1 to get first corner on bounding box, and then after that you want to move along same line, distance, and this time it's just minus 0.35 times d1, and that's because you want to go in the opposite direction. Okay, so now we have these 2 points, and so corner points should just be we'll just call them, so there's 4 corners obviously, x, so this is x sub c1, y sub c1, and then I guess I'll just copy that 4 times. Okay, this one should be c4, c4, c3, c3, and c2, c2. So now I have the corner points, and I'll just call it the first corner point. So the difference between the first corner point, so let's see, so it has that slope, so I guess I could just use point slope form to do y minus y1 is equal to m times x minus x1 plus b. So it should lie on the line. I know the equation of the line. I just have to find my points. Oh, okay. So the equation of the line, and you also use the distance. So use distance, and equation to get the corner point. So so I guess the first thing is that it has to lie along the line, has to lie on perpendicular line. So and I guess we could just say that that line looks like y sub p, no, just y is equal to the slope of the perpendicular line, backslash c dot times whatever the x is, and then add in the b value, b of the perpendicular line. So now we have, do a new equation, now point slope form, we get y minus y sub c1 is equal to m sub p times x minus x sub c1, and then plus b sub p. So, and then this should give us a relation between yc1 and xc1. So if we just rearrange it, then we could say that y sub c1, so multiply this whole thing by negative, get rid of that minus mpx minus m sub p times x sub c1, and then, oh, well, that becomes positive, and then this becomes negative, And then you also want to add plus y, minus y, yeah, but then that becomes plus y. And so then if I rearrange it again, you get y equals m sub p. Well, I guess that would just be the same exact thing. So, so yeah, I have that equation, y of c1 in terms of that. So that's, actually, I don't even know. I don't think that's what we want. I want a point that lies on that line. So, oh, I guess it's a simpler rule then. And the rule now is just that. So I guess I was wrong. So y of c1 is equal to m sub p, so the perpendicular slope, times x of c1 plus b sub p. And that gives us the relationship between the two. Okay. So I can relate the y corner point to the x corner point. What's the second rule? Well, the second rule is that the distance between the corner point and the red point is equal to 0.7 d1. So distance between red point and corner point is equal to 0.7 times d1. Okay. So we know that, so we can say that 0.7 times d1 is equal to the square root of y sub r1 minus x sub c1 squared, oh, minus y sub c1 squared plus something x sub r1 minus x sub c1, that whole thing squared. So that's the other rule. So then I think there should be two x's and two y's that satisfy this condition. So just if I just keep solving it, so then I could just say d1 is equal to that thing, square it to get d1 squared. That's a root, so if we square that, it could be negative or positive. I'm trying to think about how roots work. So if do the same thing here, 9 is equal to 3, but it's not equal to 3. It equals plus or minus 3. Nice. So 0.7 times d1 is not simply equal to, no, that root is not simply equal to 0.7 times d1. It's equal to plus or minus 0.7 times d1. Okay. Plus or minus 0.7 times d1 is equal to that. So if you square root 9, I'm just having trouble thinking about this. So I think the negative, no, positive of this squared is equal to that, and also the negative of this squared is equal to that. So d1 is always positive. Okay. I think basically there should be two values that give us an answer. So if I just move that over, 0.7 squared is 0.49. So 0.49 times, put it in a new equation, 0.49 times d1 squared is equal to y sub r1 minus y sub c1 squared plus x sub r1 minus x sub c1 squared. So that's just a quadratic. So something squared plus something squared is equal to something squared. So I guess I can put c1, x sub c1 in terms of y sub c1. So x sub c1 in terms of y sub c1. Then there's only one unknown here. So that's known, that's known. Okay, so x subs, so y sub c1, let's get rid of that. M sub p times x sub c1, and then plus b sub p. Okay. And then separate it out. Okay, so now if you square this whole thing, so that squared I guess you first want to square this whole thing, so do that squared minus, so plus that squared okay, then plus 2y sub r1 plus times 2 y sub c1 plus x sub r1, oops, plus x sub r1 squared plus x sub c1 squared minus 2 x r1 y r, no, x r1 x r2. Okay, plus x c1 squared. Oh man, I'm just having the hardest time thinking about this. So that's the distance. That so if we square each side, square each side 0.49 times d1 squared is equal to actually just this whole inside thing. So x sub c1 and y sub c1. This is just going to be a big ugly thing. So take out the y sub c1, make that x sub c1. Okay, now that whole thing, don't need these parentheses. Two x r1 x c c1, not r2. So 2x r1 x c1 2x c1. So now taking this and then grouping terms. Okay, so let's group it together. Actually separate. Oh my gosh, this is going to be an ugly term. I'm going to do this by paper real quick. Okay, so m times x. Okay, get that whole thing squared. Oh, this actually won't be bad. I thought it was 3 terms. So m sub p squared x sub c1 squared plus 2 bp m p x sub c1 plus bp squared. Okay. Okay, so let me write that down real quick. So when we separate out this term, Get rid of that parenthesis. Now, when this gets separated out, m sub p squared times x sub c1 squared plus b sub p squared plus 2 m sub p times b sub p times x sub c1. Okay. So that's that whole ugly thing. And finally, we can group it. So, x, insert equation. So you can say x sub, oops, insert equation. So x sub c1, x sub c1, quantity squared, okay, and then this term gets multiplied by a. So a is just m sub p squared. So that's pretty easy. X squared plus something times x. So the something times x would be 2 m sub p b sub p. That's the first term linked with the x right here. And there's just this x. So 2 m sub p b sub p plus 1. So that's that. Oh, x sub c1. Oh man. X sub c1. 2 m p b p minus 2 times 2x sub r1 minus 2x sub r1, and then x sub c1 also has a squared term, so this is m sub p squared and then plus 1 times x sub c1 equals that. Okay, now we have the terms linked to x sub c1, not x sub c1 squared, so x sub c1 terms, 2mp bp, got that, and then the minus 2xr1, got that. Okay, and all we're left with now is the c terms, so anything that's not linked to an x sub c1, so y sub r1 squared, got one of those. Looking over here, then there's this plus b sub p squared, only 1p, okay, plus b sub p squared. That term is linked, it has an x c1, this one doesn't, so then plus 2y sub r1 times y sub c1. Oh gosh, dang it. Get rid of that. So this y sub c1 is really this value. So y sub c1. So this should be 2y r sub I times m sub p times x sub c1 plus 2y sub r1 2y sub r1 times b sub p. Okay, so plus b sub p squared, got that term. Now this term's linked, oh, those terms are linked to the x sub c1, mp, bp, and so the other x sub c1 will be 2 2y sub r1 plus 2y sub r1, 2y sub r1, m sub p, oh, that's it. And then this is y sub r1 squared plus b sub p squared. That term's linked, that term's linked. This term is not, so then plus. That term's linked, that term's, so plus 2y sub r1 b sub p. Okay, so that's the terms, that whole thing. Oh yeah, and then we have to minus 0.49 d1 squared. And that whole thing is equal to 0. So now we need the quadratic formula. Everything's yr1, xr1, yr1. So we can replace the mp with m, bp with b. X sub r1 is equal to x, and y sub r1 is equal to y. And now we just have to use the quadratic formula. I think Wolfram alpha will do it. Quadratic formula solver. So a times x squared, so the x. Yeah. Okay. So what is this? Yeah, here's the form. So the a is m squared plus 1. B is this term right here. So we have 2 times m times b plus 2 times ijk xyz. So x is I and y is j. So m times b plus 2 times j times m, 2 times m times b plus 2 times j times m minus 2 times I, because it's x sub r1 times x, and then c is y sub r1, so j squared plus b squared plus 2 times j times b minus 0.49 times d squared. Okay, let's see if this works. Oh, good. Yeah, so x is equal to plus or minus. Oh man, no. Why is this? What is the? I think that should. Why won't it copy image? Okay, I'm just gonna paste it in here. solving with Wolfram Alpha. Okay, I'll be right back. I'm going to take a break. Okay, so now the problem I have with this one is the solution has the imaginary term in it. I'm not sure how to get rid of that. I know it has something to do with trigonometry, but I came up with a better solution. I just have to think about it real quick. So, so I have the equation of the perpendicular line. I'll just say technique 2. So I have equation of perpendicular line, have equation of center line. That's what I'm going to call it now. I'm just going to say that center line is between two end points of have equation of center line which is between two endpoints of the Bezier curve. Okay. Get equation of line parallel to center line. Get equation of line parallel to center line offset by 0.7 times d1 by adding slash. So instead, we're going to say get equation of the two lines that are parallel to the center line, offset by 0.7 times d1 by adding slash subtracting 0.7 times d1 to the b intercept. And then the four corners of bounding box should be the intersections between, I'm gonna call these steps, so that's step 1, step 2, step 3, and step 4. Okay. Corners of the bounding box should be the intersections between lines in step 3 and perpendicular lines associated with the red points. Cool. So, perpendicular line intercept 1 and perpendicular line intercept 2, they each have the same slopes. So, endpoint line slope, endpoint line intercept, perpendicular slope, perpendicular line intercept 1, perpendicular line intercept 2. So I have two lines. I have the perpendicular line intercepts. I have the perpendicular line slopes. Okay. Now, I'm gonna call this parallel line intercept 1 is equal to endpoint line intercept plus whatever the distance, so dist between points, distance between points, nice, and then parallel line intercept 2, line intercept 2 is equal to well, it should be the same as the previous line, except there's a minus sign between the terms. Parallel line intercept 1, parallel line intercept 2. So if we're trying to equate two lines, and the two lines are y1 equals m1, none y equals m1 times x plus b1, and the other line is y equals m2 times x plus b2, then you want to say y equals y, which means that m1 times x is equal to m2 So m1 times x plus b1 is equal to m2 times x plus b2, and we also have the condition that x is equal to x, so x times equation x times m1 minus m2 is equal to m1 minus m2 is equal to b2 minus b1, and now we could say that x is equal to the fraction, and on top is b2 minus b1, and on bottom is m1 minus m2, and then comma, and then y is equal to well, then just solve y from there. So corner 1 x is equal to parallel line intercept 1 minus so parallel line and perpendicular line intercept 1 divided by m1 minus m2. So that means the parallel slope 1. Oh, but so that endpoint line slope m1. So parallel line intercept 1. So m1 is the endpoint line slope. And then minus m2, which is just perpendicular line, perpendicular slope, perpendicular slope. And then corner 1y is equal to parallel, well, we could say endpoint line slope times corner 1x plus parallel line intercept parallel line intercept 1. Parallel line intercept 1. So that's corner 1. Then corner 2x is equal to so parallel line intercept 2. That's perpendicular line intercept 1. Endpoint line slope minus perpendicular slope. Okay. Then we could say corner 1. Corner 1x endpoint line slope times corner 1x parallel line intercept 1. Should be corner 2y corner 2x parallel line, intercept 1. Okay, and do the same thing for the parallel line, intercept 2. Parallel line, intercept 2. So copy that whole thing. Okay. Okay, so this is now corner 3x, corner 3y, corner 4x, corner 4y, corner 3x, parallel line, intercept 1, and it should be perpendicular line, intercept 2. Nothing to change over here. Here should also be perpendicular line, intercept 2. And cool. So corner 1 is equal 2, corner 1x and corner 1y, and it should be that for all of them. Okay, corner 2, corner 2, corner 2, corner 3, corner 3, corner 3, and corner 4, corner 4, corner 4. Now, let's see how they do. So corner 1, corner 2, corner 3, corner 4. Then draw that second red dot. Then turtle dot pick up. Turtle dot go to corner 1. Turtle dot go to. So I guess then put down after we go to corner 1. Then turtle dot go to corner 2. Then go to corner 3. Then go to corner 4. And finally, go back to corner 1. And let's see how this looks. Okay, run it. Second red point 2. Oh. So this is just red point 2. Cool. Okay, now run it again. Okay. Draws the corners. It draws the stuff no problem, but gets lost when it comes to time to draw the rectangle. Yeah, it draws those really well. Okay. Now I'm just going to start printing the corners as well. Print corner 1, corner 2, corner 3, and corner 4. Oh. I don't know. Print the values, what's it look like? Oh. Guess I didn't add that yet. Print, 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 print. Save. Run again. What's it look like? Okay, so the corners, minus 127, 237, 61, minus 5, minus 127, 237. So corner 1 and corner 3 are the same. Corner 3x. Parallel line intercept 1 minus perpendicular line intercept 2. Oh. So this should be red point 2. That should be red point 2. Okay. Now, I don't think this will work. But just out of curiosity, let's see what it does. Okay, so the corners are wrong. Try it again. Okay. Now I'm going to look through this real quick to make sure it's right. So, corner 1x. Let's see, make sure this is right. So, corner 1x. So the y is equal to each other. M2x plus b2 equals m1x plus b1. If the x's are the same, then x times m1 minus m2, b2 minus b1 over m1 minus m2. Yep. So b2 wait. b2 minus b1, so perpendicular line intercept 1. So parallel line intercept 1 minus perpendicular line intercept 1. So then you should do parallel line slope. Oh, m1 minus m2. So then it should be perpendicular line slope minus endpoint line slope. So if we put negatives in front, see if that could be a quick fix that works. Nope, still wrong. So this should be minus endpoint line slope. This should be plus. Minus. Okay, so then parallel line intercept 2 minus perpendicular line intercept 1 over perpendicular slope minus parallel line intercept. It's just the endpoint line slope. Endpoint line slope times corner 2x plus parallel line intercept 2. And then this uses parallel line intercept 1. That should use parallel line intercept 2. Okay, now, how does this look? Oh, that looks good. Except it's drawing the wrong corners, and it's not. That line that's supposed to be perpendicular is not perpendicular. Let's slow down the speed, see how it draws the stuff. So take the speed back down to 1. And let's run it. How's it look? 4. Damn it, I wasn't paying good enough attention. So, okay, boom, 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 and then 1, 2, 3, 4, 1. 1, 3, 4, 2, 1. 1, 3, 4, 2, 1. 1, 3, 4, 1, 3, 4, 2, 1. Okay, now let's look at how that looks. One, 3, 4, 2, 1. Those are all the same points now. Okay, let's watch this again. Oh, well that's not at all what I was trying to draw. So in one orientation it looks close to a box but off. No, this just looks totally wrong. Okay, so how do I do the perpendicular slope? Perpendicular slope, n.2 is 0 minus n.1 is 0 divided by n.2 of 1 minus n.1 of 1. Whew, that seems like a good slope. Endpoint line intercept. So y equals mx plus b. Y minus mx is equal to b minus endpoint line slope times x endpoint 2 y value of endpoint 2. So if the endpoint line intercept is wrong, that could only be because the endpoint line slope is wrong. And to get the slope, you do the difference in y's divided by difference in x's. 0.2. That's right. Endpoint line intercept. Perpendicular line intercept 1. Plus parallel line intercept 1. Corner 1y is equal to endpoint line slope times corner 1x. Man, I don't get what I'm doing wrong here. So there's obviously this parallel line. Instead of connecting with this parallel line, it seems like If you were to draw a line between these points, what are the corners? Yeah, so the corners have the same y values, but different x values. Why would the corners have the same y values? Corner 1y, corner 1x. Aha! That should be corner 3x. This should be corner 4x. Now, let's do it again and see what happens. Yes, that's exactly what I wanted. Almost. Well, it's closer to what I wanted. The next question is, well, I don't know, because this is almost up or down, but those look horizontal. But I guess I'll have to get one that's not exactly up or down to be able to tell. Whoa, that's way out of place. Oh, so that's what I want, but what's the problem? It should be shifted. Oh, there's something wrong with how I'm doing the perpendicular lines. Those aren't perpendicular. That's not perpendicular. Maybe it's negative inverse slope. I think that is it. So perpendicular slope is equal to negative of that. And yeah, I guess I'll just do that the same. Oh, those were too close together. Nice, now that's the right perpendicular line. I just have to figure out which way to do the corners. So, 1, 2, 3, 4, too slow. Need a bigger one. Maybe the distance. So 1, 2, 3. So it should go 1, 3, 4, 2, 1. 1, 3, 4, 2, 1. Okay, how does this one look? Nice. Now, is this perpendicular? I guess it is. Yeah. Okay. So, I guess I'll change it to blue for the first bounding box. And turtle dot pen color blue. Go to corner 1 before we put down turtle dot pen color. Should be blue. Okay, no. Nice. That's exactly what I want. Although the bounded box should be a little bit bigger that away. How much am I offsetting those distance between points equals endpoint line intercept plus distance. What? Well, the distance between points is this. Parallel line intercept 1. So I wonder if each one of these boxes that it draws are different proportional dimensions. So why is that different every time? I mean, that seems right. That seems right. Gonna run it a few more times to make sure. And now that's the issue. So it depends on how horizontal it is. When it's straight up vertical, the bounding box is way too small. It's because I'm taking the midpoint and I'm saying, okay, these parallel lines should be up here and down there. It has to do with how vertical it is. That one seemed good. So I wonder how you offset it by that much. If we want the distance between this line and that line to be some amount, then the slopes should be exactly the same. Yeah, the slopes should be the same, and the only thing you could really change is the y-intercept. So what's happening on those ones where it's up and down and you get that? It's not offset by the amount. Parallel line intercept 1 is equal to endpoint line intercept plus or minus distance between points. That looks like a good shape. Okay, now we want to know, how do we generate Python generate random point inside bounding box? Oh, nice. Now you could do shapes. Put spaces after commas. Oh, style. Shoe semicolons. 1 points is less than num points. Random point. Okay. Now, our polygon is bounded by these points. So, I'm going to import this polygon like this guy does here. See if I have shapely. Okay. From shapely dot geometry, import polygon point. Okay, so bounding box is equal to polygon of, should be a list, corner 1, corner 2, corner 3, corner 4. Now, np.random.uniform, np.random.uniform, return points, control point is equal to random points within of bounding box. I only want 1 point, the 0th item. Okay. Then go to corner 1, then turtle dot pickup. Okay. And then we're gonna go to the control point. And then we're gonna draw a dot. Turtle dot dot. 20 and so we'll make that brown. That should be blue. Okay. Now, if we run it, oh, there we go. Now it's gonna be slow. Go to control point, import pdb dot set trace. Pick that up, put it in there before the line. Now it should be good. So what's control point look like? Okay. Now let's look at it. Shapely, geometry, point. So if we go to points, point.area, point.length, points.chords. Okay. Point.chords, not a method, just an attribute. Okay. And then let's increase the speed so we don't have to wait forever. Okay. Run it. Go to vector view. Dot chords. Okay. Put this as a tuple. Tuple of control point dot chords of 0. So tuple of control point dot chords of 0. Take that line out. Cool. Okay, awesome. So now we have code that, well, I'll make it slower so it's nicer to look at. Speed should be 1. Okay, now I have code. It creates 2 endpoints, draws a line between them, draws where the bounding box should intersect, then it draws the bounding box, and then it generates a control point that's in between those 2 points. So now the bounding box, now it's going to generate the control point that should be in there somewhere. Boom. Okay, so then the next step is use this control point to make a quadratic Bezier between the endpoints. Okay. Now, how to make a quadratic Bezier. I'm pretty sure I had some code that did this. Well, I had the code I copied. I think patbez is where I do it. Endpoint, control point, quadratic point, two-sided concave. Endpoint line x from y. calculate initial curve. Dot calc x. Okay. Self dot initial points. So I kinda have some code that does it. Calculate points. Okay. So we have a Bezier curve. First and x. Okay. So initial points dot first n dot x plus 2 times t times the control point x, comma, don't know how that would work. So I'm just gonna look up the equation online. So Bezier curve, quadratic Bezier equation. Nice, calculate points. Quadratic Bezier formula, B of t. Nice. Okay, so bounding box now. Okay, control point. So now calculate points along Bezier curve. So I'm gonna do define calculate points Bezier points, and we should get endpoint 1, which is a tuple, endpoint 2, which is a tuple, and control point, which is also a tuple. Okay, now x1 equals end point 1 of 0. Okay, now we get the x's. So x1, there's also x2 and x3. So x1, endpoint 1 is 0, x2 is endpoint 2 is 0, xc is control point of 0. Okay. Same but with y's. Okay. Okay, now we have the x's, we have the y's. And what's the equation look like? So 1 minus t, 1 minus t. p0 dot x. Okay, so for get an empty list of the points. Now for t, o t array is equal to np dot a range. I guess this should be granularity, so should be an int just equals 100. Granularity t array. So for t in t array, x is equal to 1 minus t times 1 minus t times 1 minus t times start point of x, so x1 plus times x1 plus 2 times 1 minus t times t times x2 plus t times xc. Oh, no, xc, x2. Okay. And then y is just the same thing as that, but with y's instead of x's. T1 minus t, that should be y1, 1 minus t, xc turns into yc, and x2 turns into y2. And then we could do points dot append, and we want to make it a tuple of xy. Okay, and then return points. Okay, now Bezier points is equal to calculate Bezier points, and point 1 is equal to end point 1, end point 2 is equal to end point 2, control point is equal to control point, granularity is equal to 100. Okay, now turtle dot pickup, and then turtle dot go to, and then Bezier points of 0, and then 4 point in Bezier points. Okay, so this should draw the curve now. So first I'm going to look up color options in Turtle. Wow, that's nice. Cornflower blue, deep sky blue, cyan. So turtle dot pen color cyan. Okay. Now, what's that look like? Oops. Line 96. Single shape. Control point is equal to that. Okay, so something's wrong with the points I'm trying to plot. I'm going to try to go in and look at the points, see what they look like. No, now I gotta wait for it to draw. Okay, now it's gonna make the bounding box. And then draw the control point. Okay. So let's go to Bezier points of 1. That seems fine. Line 146. And go to point. Okay, let's just look at Bezier points. What's that list look like? So why does it get so big? It seems like it's going fine. The bounds of this are... Yeah, so it should be somewhere in there. Now we've gone to... Bezier points. Bezier points. Calculate Bezier points. x1 equals n.1 of 0. Okay. T array equals np dot a range. Granularity 1 minus t times 1 minus t times x1 plus 2. Just gonna double check the equation to make sure that's right. 1 minus t1. P0 is the start point, P2 is control point. Oh, t goes from 0 to 1. So divide that by granularity. Now, just to make sure, let's look at what this looks like. So import numpy as in p, np.arange 100, divide by 100. Nice. Oh, plus 100 divided by plus 1 divided by 100. What's that? Oh. Okay, so now I have t values that will go from 0 to 1, so the way to do that is just with that code. Here 100 is the granularity, so granularity plus 1 divided by granularity, and then do that whole range divided by granularity. And that should work. Okay. So if we exit, try to run that thing again. Nice. Okay, so let's take out that debugger line. Okay, run it again. Let's make the speed faster so it doesn't take forever. Okay, run it again. Nice. So, yeah, it generates the endpoints. Oh, I guess I'll go through it. So I guess I will change that back to 1. So what this does is first it generates endpoints in orange, endpoint 1, endpoint 2, draws a green line between them, then draws where the midline is going to intercept the bounding box. Then it goes and draws the corners of the bounding box. And then it generates randomly a control point that's within the bounding box. And then it draws the Bezier curve that's associated with that control point. And real quick, I'll just run this a few times. So I think that's going to be all I do today. And then next live stream I do, gonna put some more constraints on that so that it can generate some nice curves. You can see all these curves look really similar. Also gonna figure out how to draw this bounding box so that this dimension is constant. It's kind of this length, this perpendicular length right here, changes according to how vertical the green line is. So if the green line's perfectly vertical, it's tiny or nothing, and if the green line's perfectly horizontal, it's very large or infinite. So maybe I could demonstrate that here. There you see, again, when it's really close to the midline, it doesn't look good. So there's going to need to be an inner bounding box. Something like that says, okay, the control point has to be outside of the inner bounding box. And draw it again. Nice. Nice. So then, so it's gonna, so draw outer bounding box, draw inner bounding box, get control point, and then the next thing to do will be generate the second or I guess it would be the third and fourth bounding boxes, and generate a second control point. And then where the second control point should be such that the curves don't overlap, and then put the second control point somewhere in a random point, and then draw the second Bezier curve, fill it in, and now there's shapes. So that's all there is for today. Thanks for watching this live stream. Hope you liked it, and hopefully I can make more good progress next live stream. Thanks for watching. Bye.